We're now going to cover differentiation, and in this video we're going to look at an introduction to differentiation as well as how we differentiate from first principles. So, what is differentiation about? Well, differentiation is about finding gradients to start with, and that's how we're going to look at it geometrically. We know that to find the gradient of a straight line, we are interested in how that line changes in y in relation to how it changes in x. So I would look at the change in y, which I'm going to notate as delta y, over the change in x, which is denoted as delta x. So if I wanted to find the gradient of a straight line, I know I'd look at the change in y divided by the change in x. That's something quite straightforward to do. We can pick 2 points and then find the gradient. The bigger question is, what do we do when we're not dealing with a straight line? So here we have a function, a cubic function, where quite clearly the gradient is changing. In fact, the gradient is different at all points on this curve. So what do? Well, I look at drawing a tangent, like so, which will share the gradient of this curve at the instantaneous point. And I can see that just by moving this point, I can change the value of the gradient. So the gradient here is somewhere around 0. The gradient here starts to become negative. It becomes more and more negative, and then it becomes less and less negative. And at this point, the gradient of the curve would be 0. And we get this just by looking at the tangent. And on this side, the gradient is then going to increase. It's going to get larger and larger and larger, and so on. So when we're looking to find the gradient for a curve, we're actually looking to find just its instantaneous gradient, or the gradient of the tangent at that point. That's all well and good, but how do we actually go about doing that? Well, we have this nice little method. So here I've got a little function, and on this function I've drawn a chord between these 2 points. So I'm going to call this point x, and this is a point a little bit further away, so I'm going to call that x plus a little bit of x, which is a delta, but a different kind of delta, a lowercase delta rather than uppercase delta. Now let's have a look at what the y values would be. Well, if this is my function f of x, then to find the y value at this point, I would have f of x, and to find the y coordinate at this point, we would have f of x plus delta x. Now, if I want to find the gradient of this chord, the straight line between these 2 points, I would look at doing the change in y divided by the change in x. The change in y is going to be the larger y value, f of x plus delta x, minus the smaller y value, divided by the corresponding x point, subtracted x. So the difference in y this way, divided by the difference in x this way. So exactly what we know about doing straight lines. Now here's the trick. At the moment, this isn't going to give me a very good approximation to the tangent, but this approximation would get better if this point were to move closer to the point where I'm finding the gradient. So if I move this point to here, I would then have a chord, something like this, which would better share the gradient at that point. In fact, I could move it closer and it would even better share the gradient at that point. I could move it closer and it would even better share the gradient at that point, and so on and so on and so on. Well, this is something that we would call in mathematics as taking a limit, because what I'm looking at doing is moving this x point closer and closer and closer and closer and closer to the x value itself. Or in this case, making the value of delta x smaller and smaller and smaller and smaller. So we do this in mathematics by taking limits. So I want to see what happens as delta x tends towards 0. As that value gets smaller and smaller and smaller and smaller, what happens to f of x plus delta x minus f of x all over x plus delta x minus x. And remember, this is just the change in y over the change in x. And I want to examine what happens as x tends towards 0. As delta x tends towards 0, sorry. Let's have a look at that in practice. So in the top right hand corner here, I have my equation that we've just developed. And now I'm dealing with a specific function, in this case y is x squared. So how would I apply that? Well, let's just use that equation that I've got. I want the limit as delta x tends towards 0 of the function applied at x plus delta x. So that would become x plus delta x squared, because my function here is just simply the squaring function, subtract x squared, the function applied at x, and I want to divide that by x plus delta x minus x. Well, let's start off. X tending towards 0. We can deal with the denominator fairly easily because x plus delta x minus x is just going to leave me with this delta x value on the bottom. On the top, I'm going to expand the bracket, so that's going to give me x squared plus 2 lots of x times delta x plus delta x squared, and then I've got this minus x squared from the second part. Now we can see that we're going to get a cancellation of my x squareds, and if I divide through by delta x, that's going to divide through like so. So what I end up with here is the limit as delta x tends towards 0 of 2x plus delta x. Now what do I do? Well, now I apply this limit. I let delta x tend towards 0. I let that become smaller and smaller and smaller and smaller, and I see what this function would become. Well, the smaller delta x gets, the more insignificant it becomes, and if I'm adding something insignificant to 2x, it's going to get to a point where I can't really distinguish the difference between that and 2x itself. So I think the gradient of this function we've proved now to be 2x. What do I mean by that? Well, if I wanted to find the gradient at any point on that function, let's say if I wanted to find the gradient at the point where x was 3, then I just use this equation. 2 times 3 gives me 6. So the gradient at 3 would be 6. We'll look at that in a bit more detail in a later video. Let's look now at another generic example. So this time we're looking at a cubic, and we're going to apply the same logic. So I'm just using my rule, the limit as delta x tends towards 0 of the function applied to x plus delta x. So that's going to be, in this case, a lots of x plus delta x cubed minus ax cubed all over x plus delta x minus x. So again, we're going to deal with the bottom first of all, because again that's just going to become delta x, the x's will cancel out. There we go. And then I'm going to leave that a out the front and expand my bracket. So remembering how to do this from binomial expansions, this becomes x cubed plus 3 lots of x squared delta x plus 3 lots of x delta x squared plus delta x cubed, and then from that I want to subtract ax cubed. So longer expression this time, and we can see what's going to happen here. It's the limit as delta x tends towards 0. Well, if I multiply that bracket out, that's then going to give me ax cubed plus 3ax squared delta x plus 3ax delta x squared plus a delta x cubed minus the ax cubed all over delta x. Now I look at what's going to cancel. Well, I've got the same term here and here, so they will subtract. Now if I divide this through by delta x is going to disappear from here, the squared's going to disappear from here, and this is going to become to the power of 2. So what I'm dealing with is the limit as delta x tends towards 0 of 3ax squared plus 3ax delta x plus a delta x squared. Now I apply my limit. Well, if I let delta x tend towards 0, if I let that become smaller and smaller and smaller and smaller, no matter what I'm multiplying it by, delta x will eventually be so insignificantly small that it doesn't matter what I multiply it by, it will still barely exist. That's how small delta x is going to become. It's going to become so small as to be insignificant. So if I multiply, no matter how large this number may be, by something that small and insignificant, I'm just going to ignore it. And this is just a very, very small and insignificant number. So what we're left with here is 3ax squared. So this time we found the gradient of this function to be 3ax squared. Well, let's review what we've done here. So for the first function we looked at, the gradient turned out to be 2x. For the last function that we looked at here, the gradient turned out to be, on here, whoops, hopping around all over the place, 3 2ax squared. It shouldn't take too much of a leap of faith to realise if I take the generic gradient of the first function, what I'm going to end up with is 2ax. In mathematics, we love spotting patterns and we love seeing how things work, and it seems to be that the indice here is popping out at the front. So this 3 pops down to be 3, the 2 pops down to be 2, and that's exactly what's happening. And it also seems like the indice is reducing by 1. We really know that x by itself is just x to the power of 1, 3 reduces to 2, and so on. This gives us a nice way to come up with a general rule for this, which is as follows. Let's say I've got any polynomial in x, so ax to the power of n. If I want to find the gradient of that function, if I want to differentiate that function, then what I do is I bring the n to the front of the expression, and then I reduce the indice by 1. This notation that we've got on the front here, dy by dx, is the differentiation of y with respect to x. And this is how we would write down the gradient function. Incidentally, earlier where we talked about evaluating the gradient at the point where x was 2, I can write down dy by dx evaluated at the point x equals 2. All this means is I'm going to substitute 2 into this expression. We have a different notation for this if we're using functions. In functions, we tend to talk about f prime. So if this is my original function, f of x is the same polynomial, then if I differentiate it, what I end up with is f prime of x. And as we said before, we bring the indice to the front, and then we reduce the indice by 1. And that's where we're starting our differentiation.